Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So today's question is permutation counting. In this question, we're given two integers n and k, and for this version of the problem, k is a constant which is equal to 3. Now, all we need to do is count the number of permutations p of consisting of integers 1, comma n, which satisfies the following condition, which is p of I plus p of I plus 1 modulo k is not equal to 0 for all the possible values of I. And since the answer may be very, very large, we need to output it modulo this number. For instance, let's say we have a permutation like 3, 1, 2. Now this is not a valid permutation because 1 plus 2 is 3, which is divisible by 3. Or let's say there's some other permutation like 1, 3, 2. This is a valid permutation because 1 plus 3 is 4, which is not divisible by 3. And 3 plus 2 is 5, which is again not divisible by 3. Now let's see the constants ones. So in the constants, we're given that t will be as big as 10 raised to the power 4. N will be in between 2 and 2 into 10 raised to the power 5. And k will always be equal to 3. And the sum of n over all test cases never exceed 2 into 10 raised to the power 5. So we need to come up with an of n or of something like n log n or something of this order solution, right? Now let's once see the sample inputs. In the first input, we are given n equal to 2 and k is 3. Now the only possible permutations are 1, 2 and 2, 1. And none of them is a good permutation because 1 plus 2 is 3, which is divisible by 3. And here also 1 plus 2 is 3, which is divisible by 3. Now in the second test case, we are given 3, 3. And the valid permutation, the only valid permutations are 1, 3, 2 and 2, 3, 1. Because here 1 plus 3 is 4, which is not divisible by 3. 3 plus 2 is 5, which is also not divisible by 3. And similarly, that is the case here as well. Now you can just try out the rest of the test cases by yourself and I'll move to the solution. So yeah, now let us begin by writing some permutation. So let's say this is some permutation given to us and this is the modulo 3 of each of these numbers. So 7 modulo 3 is 1, 6 modulo 3 is 0 and so on, right? Now can we see that like if 6 plus 3 is invalid, if 6 plus 3 is divisible by 3, then the 0 plus 0 will always be like will also be divisible by 3 obviously, right? So basically like what I'm talking about here is that if a of I plus a of I plus 1 modulo 3 is equal to a of I modulo 3 plus a of I plus 1 modulo 3 whole modulo 3, right? This is like a very, very well-known property. So obviously, if we just take the modulus of this number and then check it, it's not really gonna matter, right? So only a of I modulo 3 matters, right? So we can just, instead of doing this, we just take modulo 3 of each of them and just count the number of possibilities in that, right? So the question is like, why not we just convert A into the array of 0, 1, 2 by taking modulo 3 of each number and then the count the number of possibilities you can get in that. But will the number of permutations in A, like the number of possible good arrays you can get in A, be equal to the number of good possible arrays you can get in this transformed array? So if let's say this is our array A, and this is our transformed array where we took modulo 3 of all of these numbers, will the number of good arrays in this and this be equal? No, obviously, right? Because here, this and this, these two elements are considered the same. But in our original array, these two elements were considered completely different. So this is going to count this 1, 2, 0, 1, 2 and 1, 2, 0, 1, 2 as same. But this will count 1, 2, 3, 4, 5 and 4, 2, 3, 1, 5 as two different arrays, right? So, but still, if we somehow calculate for this, if we calculate for this, can we get the count for this? Is it possible? And yes, it is. Why? How? So all we need to do is calculate the number of possible good arrays in this and multiply it with C0 factorial times C1 factorial times C2 factorial. And what are these C0, C1, C2? The count of zeros, ones, and twos respectively. Now, why is this going to work? So think of it as we can swap all of these ones, right? So we have something like 1, 0, 1, 2, 1, 1, 2, 1. We have some number of ones, some number of twos, and some number of zeros, right? And we can just place these ones in any possible order we wish, right? So there are like 5 factorial ways to rearrange these ones. Then there are 2 factorial ways to rearrange these twos, and 1 factorial ways to rearrange this zero. And this is the number of ways we can get, which will convert to the number of good arrays we can get in this transformed array to this normal array, right? So what we're going to do is we're going to work on this transformed array from now. And in the end, whatever answer we get, we're going to multiply it with this thing. That's it. Now let's consider this transformed arrays. We only have zeros, ones, and twos, right? So we know that 0, 0 cannot be together because it's going to be invalid because 0 plus 0 is modulo 3 is equal to 0, right? Now this 1 plus 2, this is also going to be invalid. Why? Because 1 plus 2 modulo 3 is 3 modulo 3, which is 0, right? So this is also invalid. And the last case obviously is also invalid, right? So in any possible good array, we'll have a configuration of something of this sort where we have zeros separated by some sections, right? We'll call them sections, right? And each section can contain either only ones or only twos, right? Each section can contain either only ones or only twos. Why? Because if we put a one and two here, it's going to be invalid. So we can place a few ones here, a few twos here, and a few ones, a few ones, a few twos, a few twos, right? And this is going to be completely valid, a completely valid good array, right? So now, what are the number of ways? Let's say we are given k sections, and we want to place, let's say, some n number of ones. Now, what are the number of ways to place n ones inside these k sections? So it turns out it is equivalent to n minus 1, choose k minus 1. Why? So think of it as we are given n number of ones over here, and we need to divide it into some k number of sections, right? So what we'll be doing is we'll place k minus 1 bars inside these. So if let's say we are placing 3 bars like this, then it's going to get divided into 4 sections where each of them have like some different number of, right? Now, what are the total number of positions for placing these bars? This is where we can place a bar. Over here, we can place a bar. And similarly, these all are the places where we can place a single bar, right? So there are n minus 1 positions where we can place a bar. And how many bars do we need to place? K minus 1 number of bars, right? So let's say we want 3 sections. So we're placing two bars so that we get 3 number of sections, right? So this is how we need to choose K minus 1 from these n minus 1 ones. So this is how we get the number of ways to place these n ones in these K sections. Right, and this is probably like the most important formula we'll be needing further. Now, how many possible sections, number of sections can we have? Right, because we need to place some zeros, right? And these zeros are the ones which divides the section. And we cannot place two zeros consecutively, right? So how many sections would be there? So either there would be like something, let's say we have three number of zeros. So either we can have, let's say, C of plus like this 3 plus 1, 4 number of sections. Why? We place these zeros in middle and we have like one section over here, one over here, one over here, one over here, right? So we got 4 number of sections like this, right? And similarly, we can have 2 times exactly C0 number of section. How? We'll place 3 zeros and we'll leave one of the endpoints. So this endpoint is free. And other possibilities, we leave this endpoint as free and this as a section, right? So we can have 2 times C0 number of sections. And we can also have C0 minus 1 number of sections. That is, we do not place, like we place both the zeros at the endpoints. So in this case, we'll be having just these 2 number of sections where I can place ones and twos. Right. Now, how to calculate our answer? So if we can calculate for each section, the number of ways to place ones and twos. Are we done? Right. We just need to sum up over each section that what are the number of ways we can place ones and twos, and we're pretty much done with it. Right. Now let's just count the ways to place ones and twos, given that we have S number of sections, right? So S can lie in between either C0 minus 1 or C0 or C0 plus 1, right? So let's say we want to place like in out of all of these S sections, we want to place ones in X sections out of them. Like so let's say total we have 5 number of sections, and for X equal to 2, we want to place like ones in these 2 sections, right? So what are the total number of ways to place them? C1 minus 1, choose X minus 1, right? As we discussed it. So if you want to place N minus 1 ones inside K minus 1 sections, there are these many ways. Now, if you want to place C1 number of ones inside X sections, these would be the number of ways, right? And now in all the other S minus X sections, which we'll call Y, want to place 2's, right? So what are the possible number of ways? C2 minus 1, choose y minus 1, right? Now, what are the number of ways to choose these sections themselves, right? So in total, we have S number of sections and we want to choose X sections out of them. So there are S choose X number of ways to choose X sections out of the total S number of sections, right? Now, what are the total number of possible arrays that we can get? C1 minus 1 choose X minus 1, this thing, multiplied by this thing, multiplied by this thing, over all the possible number of sections that we can have over all the possible values of X, right? And yeah, this is pretty much the whole solution. We need to calculate all of them, and the time complexity would be 3 times this O of n, and that's it. Now we can easily calculate these NCR thing by pre-computing factorials, the inverse of factorials, and just using our formula, right? Using this n factorial upon k factorial into n minus k factorial formula, right? In constant time. Now, the only last thing I want to mention again is don't forget to multiply this total number of ways with this thing to convert it from this world of 0, 1, 2's to the world of 1, 2, right? So yeah, this is pretty much the solution. Now let's discuss the solution code in C++ and Python. So we'll begin by discussing the code in C++ first. So let's say, so we have first of all pre-computed the factorial of all the n numbers, where n will be maximum 2 into 10 raised to the power 5. I'm computing the inverse of each factorial using this binary exponentiation. Now we're running a loop for all the test cases. Now for each test case, we are taking an input of n and k. We're counting the number of zeros, ones, and twos. You can also just do it directly by doing like n c upon 3, c plus 1 upon 3, sort of stuff. But yeah, now we're running a loop. We're running from C0 minus 1 to C0 plus 1. And then if S is equal to C0, we're counting it, like adding it up 2 times. Otherwise, we're just adding it up 1 time, as we discussed earlier. Now we're running a loop for X from 0 to S. Now Y is S minus X. We are just adding our answer, that is NCR C1 minus 1, X minus 1, C2 minus 1, Y minus 1, and X comma X. Then in the end, we're multiplying it with the factorial of C0, C1, and C2, and just printing an answer. Now, the overall time complexity again is big O of n, and this is pretty much the whole solution in C++. Now, let's discuss it in Python. So, we have defined this mod and this n. We have defined binary exponentiation. We have defined this vector and inverse of function. We have defined the NCR function, which will calculate the NCR. Now, we have also defined this multiplication function, just to make our calculation easier so that we don't need to like handle the modulo separately. So I'll just call this multiply function. It will just give us a multiplication modulo thing. Now we are pre-computing the factorial of I and the inverse of I for all the possible values from 1 to 2 into 10 raised to the 5. We're calling this solve function for each test case. We're taking in the input. We're counting the number of zeros, ones, and twos. Now we're calculating our answer for S in between C0 minus 1 to C0 plus 1. We're running S from 0 to S. The Y would be nothing but S minus X. Now our thing which we need to add is NCR C1 minus 1, X minus 1, C2 minus 1, Y minus 1, and S comma X, as we discussed. We'll be just adding it into our answer. Now if S is equal to C0, we need to add it twice, as we discussed, right? Because this thing would be counted 2 times. We can place 1 0 here and leave a section here, or we can place 0 here and leave the section in the starting, right? Now in the end, we're just multiplying our answer with factorial of C0, C1, and C2, and we're just printing our answer. Now the overall time complexity of all of these things is big of n, right? But one thing I want to mention in the end is the overall time complexity is n log n, because we're calculating the inverse in logarithmic time, right? Log n time for each n. So the overall time complexity for the solution is n log n, but it can be optimized if we just try to calculate this inverse more effectively. But that is not required. So obviously n log n is pretty good. And yeah, that's it for this video. I hope you liked it. Thanks. Bye bye.